Hello everyone. Today we're going to learn how to solve a differential equation. A differential equation is any equation that involves derivatives. When we are solving a differential equation, what we are given is the equation of the derivative, and we have to find the exact function that led to that derivative. We are going to review three different things so that way you understand what I'm talking about when I mention them. One is the initial condition. This is a function value that we are going to use to solve for our constant of integration, or c. The general solution is once you integrate your equation, is the equation that we get that has the c. And then the particular solution is the one that we get when we actually have the c and we plug it in. So let's go over what this is going to entail. This is a differential equation, because we have dy dx, which is the derivative of y with respect to x, which is 6x squared plus 6x plus 2. And we are given this as our initial condition. F of negative 1 is equal to 2. In order to solve a differential equation, we have to separate our variables, meaning all of the y's and dy's on one side and all of the dx's and the x's on the other side. So here I have dy over dx. Now it may not seem like it, but we can separate the dy and the dx. This is a fraction. So in order to separate that, I can multiply dx to both sides. And this would give me the equation dy is equal to 6x squared plus 6x plus 2 dx. Now that you have your variables and your d's separated, we can integrate both sides. The integral of dy, this is like saying 1 dy, which the integral of that would be y. And this is going to equal to 6x to the third over 3, which is 2x to the third, plus 6x squared over 2, which is 3x squared, plus 2x plus c. So this is my general solution, but I want the particular solution, the one that actually has what the value of c is. So we are going to take this initial condition and we're going to plug it in. This negative 1, this is the x, and the 2 is the y. So I'm going to plug that in. Y is 2 is equal to 2 times 1 to the third, negative 1 to the third, plus 3 times negative 1 squared, plus 2 times negative 1, plus c. This is going to allow me to solve for c. And this, I'm just going to remind you, this is the general solution. This is the one we're going to use later once we plug in c. So now we're going to evaluate. We got 2 is equal. Now negative 1 to the third is negative 1 times negative 1 times negative 1, which is negative 1. And negative 1 times 2 is negative 2. Negative 1 squared is positive 1 times 3 plus 3. 2 times negative 1 is negative 2 plus c. So I have 2 is equal to negative 2 plus 3 is 1 minus 2 is negative 1 plus c. Add the 1 to both sides. We get that c is equal to 3. Once you have your c, you're going to take the c and plug it in to your general solution so we can get the particular solution. And our particular solution would be y equals 2x to the third plus 3x squared plus 2x plus 3. So this is the most basic type of differential equation and how we can solve for it. Let's look at some more examples. When looking at this first example, we have dy over dx is equal to 1 plus 12x raised to the 3 over 2 divided by 2 square root of x. And here is my initial condition of f of 4 is equal to 52. So first we want to separate our variables. Here I have only x's, so that means I just need to multiply dx over to the other side. So I have dy is equal to 1 plus 12x to the 3 over 2. And now, since everything is divided by 2 square root of x, I can put everything in the numerator over 2x to the 1/2, which is the exponent of the square root. That way, making it easier for me to rewrite my function so that I could integrate. So I've just separated my fraction. Now what I'm going to do is I'm going to rewrite this so that I can integrate. Here, this 1 over 2, I can't do anything with that, so I'm going to leave that. But this x to the 1/2, I can bring up, so that way I can integrate it, and when I bring it up, it's going to be to the exponent of negative 1/2. Then over here, we have plus 12 divided by 2 is 6. And x to the 3 over 2 over x to the 1/2, we subtract the exponents. 3 over 2 minus 1 over 2 is 2 over 2, which is 1. So that is my new exponent of x, dx. Now I'm ready to integrate it. So the integral of dy is y equals, we have the 1/2 x. I'm going to add 1 to the exponent, so that'll be 1/2, and then multiply by the reciprocal, which is 2, plus 6x squared over 2 plus c. Rewrite this one more time so that it's easier for me to plug in numbers. We got y is equal to, this 1/2 and this 2 will cancel, and x to the 1/2 is the square root of x plus 3x squared plus c. What I like to do at this point, once I have this part down, I have my general solution, I like to put a little star by it, because this is going to be my answer. I just need to figure out what c is going to equal to. So now I'm going to plug in my initial condition. F of 4 is equal to 52. That means that 52 is equal to the square root of 4 plus 3 times 4 squared plus c. 52 equals 2 plus 4 squared is 16, and 16 times 3 is 48 plus c. If I add 2 plus 48, I get that 52 is equal to 50 plus c. Subtract the 50 over, and we get that c is equal to 2. Once I have c, I can take the equation that I starred and plug it in. So y is equal to the square root of x plus 3x squared plus 2. This would be my equation, my final answer, my particular solution. Now for b, we have dy over dx is equal to x squared plus 2x all over 2y, and my initial condition is f of 0 is equal to 1. If you ever have a differential equation where your variables are across from each other, you see how you have dy and then the y in the denominator. I have dx here and then my x is in the numerator. Then what you can do to group them together appropriately is you can cross multiply. So that way on the left side I have 2y times dy, which is 2y dy, is equal to x squared plus 2x dx. And now I'm ready to integrate. 2y would be 2y squared over 2, which would be y squared, is equal to x to the third over 3 plus 2x squared over 2, which is x squared plus c. This is my general solution. Now I have here as a tip, solve for the constant of integration, meaning c, immediately after integrating and before solving for y. This will reduce the difficulty of solving for c. So what that means is here, even though my equation is not y equals blank, I can plug in my initial condition right now. It's actually easier than if you were to solve for y first in the long run. So I'm going to plug in my values now. My y is 1, so that's 1 squared, is equal to, I'm going to plug in 0, 0 to the third over 3 plus 0 squared plus c, which all this translates to is 1 is equal to, this is 0, c. So 1 is c. So now I'm going to plug it in here. So y squared is equal to x to the third over 3 plus x squared plus 1. Now this is not completely done because we want our final answer, that particular solution, to be y equals. So in order to solve for y, I have to square root to get rid of. Now don't forget that whenever you square root something, here it canceled out, so that's fine. So y equals. Whenever you square root, the answer is always plus or minus. But remember that we are looking for a particular solution, meaning there's only one. And this indicates that there's two, the positive square root or the negative square root. So what we have to do is check with our initial condition to see which one it is. If y is equal to a positive number, then that means that my answer is going to be the positive square root. So it's not the negative, we're going to discard that. And so my answer, my particular solution, would be y equals the square root of x to the third over 3 plus x squared plus 1. Let's look at these now. Here I notice once again that my dy and my y are directly across, and my dx and the x's are also diagonally across. So I'm going to cross multiply. So we got on the left, y dy is equal to 2x plus 1 dx. And now we're going to integrate both sides. The integral of y is y squared over 2. Is equal to 2x squared over 2, which is x squared, plus x plus c. So this is my general solution so far. Now I'm going to plug in my initial condition. So my negative 3 is the y, so that's negative 3 squared over 2 is equal to 1 squared plus 1 plus c. This gives me negative 3 squared is 9, so 9 over 2 is equal to 1 squared is 1 plus 1, 2 plus c. To solve for c, I'm going to subtract 2 to both sides. So 9 over 2 minus 2 is equal to c. I need to put this over 2, so I need to multiply the numerator by 2. So c is going to equal to 9 over 2 minus 4 over 2, which is 5 over 2. I'm going to take that number and plug it in for c. So y squared over 2 equals x squared plus x plus 5 over 2. Now we need to finish solving for y. So I'm going to multiply 2 to both sides. And when I multiply on the other side, I have to make sure that I distribute it. So y squared is equal to, now I'm going to distribute this 2, and I get 2x squared plus 2x, and then these 2's here would cancel, so plus 5. Our final step now would be to square root both sides. Again, keeping in mind that the answer could be plus or minus. So I'm going to check my initial condition. We see that the initial condition for the y is negative. So that means that my particular solution is going to be negative square root of 2x squared plus 2x plus 5. Now over here we have a different scenario. We can't cross multiply because we don't have the y in the denominator. So we need to figure out another way to make sure that we have the y and dy's on one side and the x's and dx's on the other. What I can do first is at least get rid of the dx from the denominator by multiplying it. So I have dy is equal to x squared square root of y dx. Finally, I can get rid of this square root of y by dividing it since everything is being multiplied. So I have now the equation dy over the square root of y is equal to x squared dx. Now if I rewrite this again so that I can write the exponent for the square root, this is dy over y to the 1/2 is equal to x squared dx. And then in order to integrate, I'm going to have to bring up the y. So that means that that exponent is now going to become negative. So it's y to the negative 1/2 dy is equal to x squared dx. I'm now going to integrate both sides. Adding 1 to this exponent would be y to the positive 1/2, and I'm going to multiply by the reciprocal, which is 2. And that's going to equal to x to the 3rd over 3 plus c. This is my general solution. I am now going to plug in the 4. So this is going to, or the 4 for the y and the 3 for the x. So this is going to be 2, and now this is to the exponent of 1/2, which is the square root of 4, is equal to 3 to the 3rd over 3 plus c. The square root of 4 is 2, times 2 is 4, equals 3 to the 3rd is 27, divided by 3 is 9, plus c. Subtract the 9 from both sides, we get that c is equal to -5. Now let's go back to our general solution and plug in the c. So 2y to the 1/2 is the square root of y is equal to x to the 3rd over 3 minus 5. First, I need to divide the 2. Now to make this easier, when we divide 2, that's the same thing as multiplying by 1/2. So I'm going to take this side and I'm going to distribute 1/2. So square root of y is going to equal to x to the 3rd over 6 minus 5 over 2. And then finally, we're going to square it. This will cancel out with that. So my final answer, my particular solution, is y is equal to x to the 3rd over 6 minus 5 over 2 squared. And you don't have to actually square that. We can just leave it. And this would be my final answer. Now we're going to look at a different type of differential equation. So if I have here dy over dx is equal to x to the 4th times y minus 2, and we have the initial condition f of 0 is equal to 0. First, I need to separate my variables. Now this is not like the one that we can cross multiply because the y minus 2 is not in a denominator. So just like the one that we did before, we are going to multiply dx to the other side to at least start the separation process. So dy is equal to x to the 4th, y minus 2 dx. And now I want to remove this y minus 2 because it has a y and move it to the other side. So I'm going to divide by y minus 2. So what I have now is dy over y minus 2 is equal to x to the 4th dx. Now with this question, it's difficult to see how to integrate this side, but I can move dy off to the side, and I can rewrite this as 1 over y minus 2 dy is equal to x to the 4th dx. Because if I multiply 1 over y minus 2 with dy, that would give me this. So I can separate it so that way it's easier to see how to integrate. So now we're going to integrate both sides. 1 over y minus 2. This looks like it could be an ln situation. If I look at the denominator, the derivative of y would be 1, and then the derivative of -2 would be 0. So the numerator is a derivative of the denominator. So this is going to give me ln, and remember when we integrate and we get ln, it's always the absolute value of what's inside, is going to equal to x to the fifth over 5 plus c. This is going to be my general solution for now. I am going to now plug in my initial condition. Just like we do with the other ones, before we solve for y, it's easier if we solve for c. So I'm going to plug in the 0. The ln of 0 minus 2 is equal to 0 to the fifth over 5 plus c. 0 minus 2 is negative 2. And because it's an absolute value, this will make it the ln of positive 2 is equal to, this is 0 plus c, so c. So now we have our c. So I'm going to take that c and I'm going to plug it into my general solution. So we have the ln of y minus 2 is equal to x to the fifth over 5 plus the ln of 2. Now, to isolate the y, we first need to get rid of ln. And how we get rid of ln is by applying e, because e and ln are inverse functions, meaning that they will cancel each other out. If we apply e to both sides, what that means is that we are making e the base, and then this is going to be the exponent, which I would have to do the exact same thing to the other side. So now e and ln will cancel. I'm left with the absolute value of y minus 2 is equal to e raised to the exponent of x to the fifth over 5 plus the ln of 2. In this situation, I know that e and ln will cancel, so I can try to simplify this a little bit. But we have this x to the fifth over 5 in the beginning, which does not allow me to cancel out e with ln because of that. So what we can do here is we can apply our property of exponents. If we have our exponents are being added together, that means that we had two identical bases, being e, with these two exponents that were multiplied together. So I'm outlined that here. If x is equal to a plus b, that means that we were if x raised to the a plus b, which is what I have here, that means that it was equal to x to the a times x to the b. Kind of like, I put this as an example, if I had x squared times x to the third, we would add those exponents, so that would be x to the 2 plus 3, which is x to the fifth. So I am going to rewrite this as e raised to the x to the fifth over 5 times e to the ln of 2. This now allows me to cancel out this e with the ln, and I'm left with 2, which is now a coefficient. So I have absolute value of y minus 2 is equal, I have this 2 that is now being multiplied. So that's 2e x to the fifth over 5. To get rid of the absolute value, this means that whatever was in here is either positive or negative. So to reflect that, we are going to write two separate equations. Either y minus 2 is equal to 2e x to the fifth over 5, so this is the positive version, or y minus 2 is equal to the negative version, which is negative 2e raised to the x to the fifth over 5. To solve for y, for each one, we're going to add 2 to both sides. So now I have these two equations. Either y is equal to 2e x to the fifth over 5 plus 2, or y equals negative 2e raised to the x to the fifth over 5 plus 2. It's up to me to figure out which one of these two is the correct answer. And I'm going to use my initial condition to help me figure that out. If x is 0, the y should be 0. So I'm going to plug in 0 for both y and x and see if I get a true statement. If I get 0 equals 2e raised to the 0, because 0 to the fifth would be 0 divided by 5 is still 0. Anything raised to an exponent of 0 would be 1. So this is 2 times 1, which is 2, plus 2. 0 does not equal to 4, so it's not this one. But I'm just going to plug it in here so you can see. If I plug in 0 for y, I get negative 2 times e raised to the 0, which is 1. So that would be negative 2 plus 2. This is true. So that means that this one would be my particular solution. Let's try another example. We have dy over dx is equal to y minus 1 over x squared, and we have the initial condition f of 2 is equal to 0. Again, this is one where I cannot cross multiply because if I do, I get dy x squared and then dx with the y minus 1. So what we can do is, well, I guess you can cross multiply and then see what we would do from there. So let's just try that out and see what happens. We get here x squared dy is equal to y minus 1 dx. But my variables don't match here. So that means that for both sides, I'm going to here divide the x squared so I can put it with the dx. So I have dy is equal to y minus 1 dx over x squared. Then to remove this y minus 1, I can divide it. Now when I rewrite this, I can rewrite it in a way so that it's easier for me to integrate. If I have dy over y minus 1, I can move the dy to the side, so it will be 1 over y minus 1 dy is equal to, and I can do the same thing here, move the dx to the side, so it will be 1 over x squared dx. Now I can start integrating. 1 over y minus 1. Check to see if this is an ln situation. The derivative of y is 1, so this is ln. ln of the absolute value of y minus 1 is going to equal, now here 1 over x squared. This is a monomial and it's not ln because the derivative of x squared would be 2x, which is not here. But I can rewrite this as the integral of x to the negative 2 dx. I can bring that x squared up. And now I'm going to add 1 to that exponent, which is x to the negative 1, divide by the new exponent, plus c. So what I have so far is the ln of y minus 1 is equal to, now anything divided by negative 1 will be negative. This x to the negative 1 means that the x goes down to the denominator, leaving me with 1 over x plus c. This is my general solution. I want to solve for c, so I'm going to plug in my initial condition. If I plug in 0 for y, I get the ln of 0 minus 1 is equal to, and now I'm going to plug in the 2, negative 1 over 2 plus c. 0 minus 1 is negative 1, and the absolute value of negative 1 is 1. So I get the ln of 1 is equal to negative 1/2 plus c. Now the ln of 1 is 0. So 0 is equal to negative 1/2 plus c. If I add the 1/2 to the other side, I get that c is equal to 1/2. So now I'm ready to start figuring out what is my particular solution. I'm going to plug this into my general solution. So the ln of the absolute value of y minus 1 is equal to negative 1 over x plus 1/2. I need to solve for y, so to get rid of that ln, I'm going to apply e to both sides, just like we did in the previous problem. E and ln here will cancel, so that'll leave me with the absolute value of y minus 1 is equal to, now here, if I separate this into its multiplication parts, just like we did here, you see how here we turn x to the 5th over 5 plus the ln of 2 into x to the 5th over 5 times e raised to the ln of 2. We only do that because we had ln part of the exponent, which can be simplified. But here I do not have ln as part of the exponent, so to turn that into e raised to the negative 1 over x times e to the 1/2 is not going to make things any better. So we're just going to leave the exponent as it is. Now I want to get rid of the absolute value, so I need to write my two equations. One for the positive version, which will be e to the negative 1 over x plus 1/2, or the negative version, which would be y minus 1 is equal to negative e raised to the negative 1 over x plus 1/2. So now the last step would be to add 1 to both sides of this equation. So I have y is either e to the negative 1 over x plus 1/2 plus 1, or y is equal to negative e raised to the negative 1 over x plus 1/2 plus 1. Now I need to make sure which one of these is correct. So we're going to plug in the initial condition and see which one works. So if the y is 0, I get 0 equals e raised to the negative 1 over 2 plus 1/2 plus 1. Negative half plus 1/2 would be 0. So this is going to be e to the 0, which we know is 1 plus 1. Now 1 plus 1 is not 0, so this is not the correct equation. But we're just going to check this one to make sure everything is good. So y is 0, so 0 equals negative e to the negative 1 over 2 plus 1 over 2 plus 1. 0 equals, now we have negative. This again is going to be e to the 0, which is 1 plus 1. Negative 1 plus 1 is 0, so this checks out. So my correct particular solution would be y equals negative e raised to the negative 1 over x plus 1 over 2 plus 1. Now we're going to look at solving a differential equation that involves particle motion. And we've done this before, you just didn't know that we were doing differential equations. So let's look at an example. We have here the acceleration of a particle moving along the x-axis at time t is given by a of t is equal to 6t minus 2. If the velocity is 25 when t is equal to 3, and the position is 10 when t is equal to 1, then the position x of t equals. So I need to figure out what is the equation. We are given two bits of information here. If the velocity is 25 when t is equal to 3, that means that v of 3 is equal to 25. This will be an initial condition for my velocity function. And here the position is 10 when t is equal to 1. Now position function here is written as x. So this is x of 1 is equal to 10. This will be my initial condition for position. We have two initial conditions because we are given acceleration. That means that in order to get position, I'm going to need to integrate twice. So I have a of t is equal to 6t minus 2. I'm going to integrate both sides, and I'm going to close this integral with dt. Because remember, in order to integrate, the integral has to be closed with the appropriate d. The integral of a of t is v of t, my velocity. And that's going to equal to 6t minus 2, which when we integrate would be 6t squared divided by 2, so 3t squared minus 2t plus c. Now v of 3 is equal to 25. I'm going to use that to solve for c. This is my general solution. So I'm going to plug it in. V of 3 is going to equal to 3 times 3 squared minus 2 times 3 plus c. And that's going to equal to 25. 3 squared is 9 times 3 is 27. Minus 2 times 3 is 6. Plus c is 25. 27 minus 6 is 21. Plus c is 25. So if I subtract 21 to both sides, I get that c is equal to 4. So my particular solution for velocity would be v of t is equal to 3t squared minus 2t plus c, which is 4. To get position, I have to integrate one more time. When I integrate v of t, that gives me position, which is x of t. And that's going to equal to 3t to the third over 3, which is t to the third, minus 2t squared over 2 is t squared, plus 4t plus c. I have my initial condition here, so I'm going to plug that in. X of 1 is going to equal to 1 to the third minus 1 squared plus 4 times 1 plus c equals 10. 1 to the third is 1 minus 1 squared is 1. This will cancel out. 4 times 1 is 4 plus c is 10. If I subtract 4 from both sides, I get that c is equal to 6. So my particular solution, x of t, is going to equal to t to the third minus t squared plus 4t plus 6. Let's look at a couple more particle motion questions. Here we have that a particle moves along the x-axis so that any time t is greater than or equal to 0, its acceleration is given by a of t is equal to 6t plus 6. At time t is equal to 0, the velocity of the particle is negative 9, and its position is negative 27. So what I have here is that v of 0 is equal to negative 9, and we'll call it p of 0 is going to equal to negative 27. So if I want to find the position of the particle at any time, that means that we are looking for the equation for p of t. So that means I have to take my acceleration function and integrate it twice. So I'm going to integrate this. The integral of a of t is v of t, and that's going to equal to 6t squared over 2, which is 3t squared, plus 6t plus c. If I plug in 0, my initial condition for velocity, I get v of 0 is equal to, this will be 0, plus 6 times 0, 0, plus c is going to equal to negative 9. So here we see that c is negative 9. So my particular solution for velocity is 3t squared plus 6t minus 9. Now to get position, we're going to integrate one more time. The integral of velocity is position function, and that's going to equal to 3t squared over 3, which will be, 3t to the third over 3, which would be t to the third, plus 6t squared over 2 would be 3t squared, minus 9t, and then plus c. Now we have to plug in the initial condition. So p of 0 is going to equal to 0 to the third, 0, plus 0 squared is 0, minus 9 times 0, plus c is negative 27. So I have here that c is equal to negative 27. So my final answer, my particular solution for the position function, is t to the third plus 3t squared minus 9t minus 27. For the second part, we're going to review how to get total distance. So it says here, find the total distance traveled by the particle over the interval 0 to 2. So remember, if we're finding total distance, that is the integral of the absolute value of v of t dt. but we don't know how to do the integral of absolute values, so we need to check first if the particle changes direction. And if it does, then we are going to integrate from 0 to where it changes and get the absolute value of that, plus where it changes to 2 and get the absolute value of that. So let's try. First, I need to check where it changes direction. Particles will change direction when velocity changes signs. So I need my velocity function, which we happen to find here in part A. You can see here before I integrated, I got that velocity is equal to 3t squared plus 6t minus 9. We're going to make it equal to 0 so we can get those critical numbers. From each of these terms, I can take out a 3, which will give me t squared plus 2t minus 3. If I continue to factor that, that will give me t plus 3, t minus 1, giving me values of t of negative 3 and 1. Now remember, t is time, so this negative time will not affect our answer. We can discard it. The only time that I have to worry about is the 1. So we're going to check if the particle changes direction at 1. Plug in a number into velocity to the left of 1. So if I plug in 0, 0 plus 3 is positive, 0 minus 1 is negative, and a positive times a negative is negative. Then if I plug in 2, 2 plus 3 is positive, 2 minus 1 is positive, and a positive with a positive creates a positive. So my particle does change direction when t is equal to 1. That means to get total distance, we are going to get the absolute value of the integral from 0 to 1 of my velocity function, which is this one up here, 3t squared plus 6t minus 9 dt, plus the absolute value of the integral from 1 to where the interval ends, which is 2, of 3t squared plus 6t minus 9 dt. Now we're going to integrate and then plug in those limits of integration. So this first part is the absolute value of 3t squared over 3, well 3t to the third over 3, which is t to the third, plus 6t squared over 2 is 3t squared minus 9t. And I'm going to evaluate that from 0 to 1, plus the absolute value of the same exact integral, so t to the third plus 3t squared minus 9t, and this one will evaluate from 1 to 2, keeping in mind that these are the absolute values. So now when I plug in the 1, 1 to the third is 1, plus 1 squared is 1 times 3, 3, minus 9 times 1 is 9. Minus when I plug in 0, but if I plug in 0, everything will be 0, so 0. Plus the absolute value of, I'm going to plug in the 2, that's 2 to the third is 8, plus 2 squared is 4 times 3 is 12, minus 9 times 2 is 18. Minus, now when I plug in the 1, 1 to the third is 1, plus 3 times 1 is 3, minus 9. Now we're going to work this out. 1 plus 3 is 4, minus 9, we get the absolute value of negative 5, plus 8 plus 12 is 20, minus 18 is 2, minus, and this we did, 1 plus 3 is 4, minus 9 is negative 5, so minus negative 5 becomes plus 5. So what this is, the absolute value of negative 5 is 5, plus the absolute value of 2 plus 5 is 7, and 5 plus 7 is 12. And this would be my total distance. And since we don't have units, we don't have to worry about adding on any units. So I wanted to review the total distance. But that is how we solve differential equations.